So imagine this. A single key that could unlock every digital secret on the planet. I'm talking bank accounts, government files, your private messages, absolutely everything. Now that key doesn't exist yet, but the race to build it is very, very real. Today we're diving into the world of quantum computing, a technology so powerful it's ready to rewrite the rules of our entire digital universe. So what's the immediate threat? Well, it's a strategy that sounds like something out of a spy movie. Store now, decrypt later. Right now, as we speak, governments and other groups are collecting and hoarding gigantic amounts of encrypted data. They can't read it yet, but they're betting that in, say, 10 to 20 years, a quantum computer will crack it all open in minutes. This means data that needs to stay secret for decades, stuff like genetic information, national security intel, or long-term corporate plans, could one day be an open book for our adversaries. And look, this is not science fiction. The National Security Administration itself, the NSA, has put out this incredibly stark warning. The very institutions in charge of our security are telling us, flat out, that the locks on our digital world are facing an existential threat. The stakes here could not be higher. To understand why this is such a big deal, we need to look at the fundamental building block of a quantum computer, the qubit. This slide shows the core difference perfectly. A classical bit, the kind in your phone or laptop, is like a light switch. It's either on or off, a 1 or a 0. Simple. But a qubit can be both at the same time. This is called superposition. It's more like a dimmer switch, existing in a mix of states. And it's not that we don't know which one it is. It really truly is both at once. The second quantum superpower is entanglement. And this is where things get really wild. You can link multiple qubits together so their fates are completely intertwined. So if you have two entangled qubits, you might not know the state of either one, but you know they're connected. The whole system just exists as this single holistic combination of every possible outcome. So what do you get when you combine superposition and entanglement? You get something amazing called quantum parallelism. Think about it like this. A classical computer with 2 bits has to check each of its 4 possible states one by one. But a quantum computer with 2 qubits, it exists in a superposition of all 4 states at the same time. This means it can perform a calculation on all of those possibilities at the exact same moment. It's not working step by step, it's exploring every single path at once. And this slide just brilliantly illustrates the insane exponential power we're talking about. The number of states a quantum computer can juggle doubles with every single qubit you add. So by the time you get to just 300 perfect qubits, you can represent more values at once than there are atoms in the entire known universe. I mean, the sheer scale of that is almost impossible to wrap your head around. But with all of that incredible power comes a huge challenge. Right? If your computer has calculated every single possible answer, and they're all just mixed together in this giant quantum soup, how in the world do you pull out the one correct answer you're actually looking for? If you just try to measure the system, the whole thing collapses and you just get a random answer, losing all that other amazing information. This is the central puzzle, and solving it takes some seriously clever algorithms. The reason this all matters so much is because of how our current security works. Most of it is based on a system like RSA. Basically, you take 2 massive secret prime numbers and multiply them together. That gives you an even bigger public number, your public key. Anyone can use that key to encrypt a message to you, but only you, the person who knows those original secret primes, can decrypt it. Why? Because trying to factor that huge public number back into its original primes is an incredibly hard math problem. And when I say hard, I mean practically impossible. To put it in perspective, it would take the world's best supercomputer about 16 million years to factor a modern encryption key. But a quantum computer running a specific program called Shor's algorithm, it could theoretically do it in minutes. So the key takeaway here is that quantum computers aren't just faster, they can solve certain problems that are completely, fundamentally out of reach for any classical machine. So how does it do this? A quantum computer doesn't just try every possible number. That would still take forever. No, the genius of Shor's algorithm is that it flips the problem on its head. It transforms the factoring problem into a pattern-finding problem. It's designed to find a hidden repeating cycle hidden in the math. Okay, so here's the simplified version. First, the algorithm creates a massive superposition, a cloud really, of a huge range of numbers. Then, through some very clever math, it engineers a situation where the correct answers form a repeating periodic pattern within that cloud. And finally, it uses a special mathematical tool that acts like a perfect frequency detector to find the period of that pattern. And that period, that's the golden ticket. It leads you directly to the secret prime factors. Game over. So, if our current encryption is doomed, what's the solution? Well, the answer isn't to stop quantum computers from being built. It's to build a new kind of lock. To fight a quantum threat, you need a quantum-proof defense, a whole new generation of cryptography that's hard for both classical and quantum computers to break. And that race is already well underway. Way back in 2016, the U.S. National Institute of Standards and Technology, NIST, launched a global competition to find these new methods. They got 82 different proposals from cryptographers all over the world, and after years of really rigorous testing, they finally selected the first set of standardized algorithms in 2022. One of the leading candidates that's emerged from all this is something called lattice-based cryptography. Instead of relying on factoring big numbers, its security is based on a totally different kind of hard problem. Trying to find a specific point within a really complex, multi-dimensional grid, or what they call a lattice. The core idea is actually best explained with an analogy, which this slide lays out perfectly. Imagine you have a good map to navigate this lattice, made of nice, simple, clean vectors. Finding any point is easy. That's your secret key. But for your public key, you publish a bad map, made of skewed, awkward vectors. They actually describe the exact same lattice, but trying to find a specific point with that map is nearly impossible. So here's how it all works. A message gets encoded as a point on the lattice, but with a little bit of noise added, so it's slightly off target. Now, an attacker, who only has the public bad map, has to search an impossibly vast number of nearby points to find the right one. But you, with your secret good map, can instantly find the intended lattice point and decode the message. And as far as we know today, this problem is incredibly difficult for any computer we can possibly imagine. So, where does all this leave us? Well, the quantum race is well and truly on. On one side, you have the teams building computers powerful enough to break our current world. And on the other, you have the cryptographers and mathematicians building a whole new world of security to keep us safe. The real question isn't just if the new locks will be ready before the keys are forged, but what happens to the decades of secrets that have already been stored away, just waiting for that one key to turn.